So today our objective is to learn how to factor by grouping. Now I'm going to put next to this that we don't do factoring by grouping when it's a binomial or a trinomial. It needs to be 4 terms. So it's a 4-term polynomial. Now, embedded in this is looking for GCMFs. Okay, so embedded is that, and embedded in that, embedded in the embedding is their exponent rules. Because when I'm factoring out, I'm dividing, so I have to divide the coefficients but subtract the exponents of like terms. So we're going to be implicitly reviewing exponent rules. And then we always have to be watchful for difference of squares. So review factoring difference of squares. So we always have to be asking those questions. Okay. So basically what we found out through that example as we were practicing is that sometimes a GCMF can be a binomial. Sometimes we must group terms 2 by 2. I'm going to write 2 at a time to find a GCMF. Okay. So what we're going to end up doing is looking for these ideas of GCMFs. GCMFs can be an individual binomial that they both share in common. They could start off that way. It could be, I forgot a word here, group terms. Sometimes we can't see a binomial, we just have 4 terms, so then we have to group them and look for something that each of the groups have in common. And then up will appear this common binomial, and we factor it out. Okay, so that's what we're going to be practicing today. I'm going to show you 2 different types of problems. One where they've already factored, are done like the first step for us, and then one where we have to go from beginning to end. Okay. Oh, and just to let you know, this comes out of our green book, and this is lesson 6-6, so the 6th lesson in chapter 6. So what's weird is we're doing things kind of out of order, but the high school had shared this technique with us several years ago and have found it very helpful for getting you guys organized, okay? Because we're going to use this technique and the technique I teach you tomorrow. All right, so let's do some examples. The directions are going to say factor, and that's implicit for factor completely, which means, hey, once you got your factors, check to see if you have any difference of squares. If you do, you have to keep going on. So let me give you a couple where the it's already been partially factored. So we have a times the quantity n minus 1 plus 3 times the quantity n minus 1. So when they've already done some of the legwork, it's pretty easy to see what they have in common. What are these 2 terms? Because 2 terms, they're separated by the plus sign. What's in front of the plus sign is a term. What comes after the plus sign is a term. What do they have that's the same? So they have a GCMF of n minus 1. So when we deal with this idea of a GCMF that's a binomial, it works the same way as if it was a single term. A monomial, we're going to divide both by that GCMF n minus 1. And if you remember, that GCMF in the answer goes right out in front. Okay? Patrick? Yeah, we guess we could. Monomials, yeah. But you know what? I think it's enough. We got GCMF. I think if we go GCBF, then we're going to That's going to be kind of nuts, but you're right. I see where you're going on that one. Okay, so when I take the first term, a times the quantity n minus 1, and I divide it by n minus 1, what's left? I have an a left. And then it says plus, and if I take 3 times the quantity n minus 1 and divide it by the n minus 1, I'm left with 3. The only factor that has a minus in it is the first GCMF, which was a GCBF, and it's not the difference of squares because n's not a perfect square. So I'm done. Okay. How about this one? 2x times the quantity x plus 2 minus the quantity 2 plus x. Okay. Do you see something that they have that's the same? Right?
Yeah, x plus 2.
Yeah. What's weird is kids will say, no, they have nothing in common, and I'll say, why? And they say, well, because one is x plus 2, the other is 2 plus x. But we have a property that you've learned for a couple different years called the commutative property of addition. And the commutative property of addition says you can change the order of what you add, and the value is still the same. Okay? Now, let's keep looking at this problem. In order for me to do this factoring by grouping, I need to have coefficients in front of the binomials. So the second one doesn't have a coefficient, but what could I put in its place to be its coefficient? Yeah. Even if I don't see it, it's there. Okay? So they do have the GCMF. Is going to be that quantity x plus 2. So I'm going to rewrite this problem since I've made a big mess of it. And I have 2x times the quantity x plus 2 minus 1 times the quantity x plus 2. Commutative property allows me to do that. I'm going to divide both of these by the quantity x plus 2. When I do factoring, the factor is not thrown out. He's a very valid part of the answer. He's out in front. And when I do my division, what's 2x times the quantity x plus 2 divided by the quantity x plus 2? What's left? Hold on. One thing at a time. We get a 2x. And then I see a minus. And what's 1 times the quantity x plus 2 divided by x plus 2? We get a 1. I look at where there's a minus. 2 is not a perfect square, so I know I don't have a difference of squares, and my answer is finished. Brian?
Does it matter which order it goes in? Because when you multiply, it's still the same answer.
Oh, yeah. The order of the binomials is not important at all, just like it wasn't when we were doing sums and differences with the difference of squares. But again, the path I'm taking is I'm always putting that GCMF out in front because that's kind of the pattern we established when we were looking for the GCMF in our first set of notes, that single value. He's usually in front. Okay, so that's what you're going to see me do all the time is put the GCMF out in front. But mathematically, you're right. The commutative property of multiplication says it doesn't matter the order that you multiply two terms. The answer will be the same. Okay? All right, let's do one more, and this one has a bit of a trick to it. So we have 4x times the quantity x minus y, and we're going to add to that 3 times the quantity y minus x. So we're looking at those binomials, and are those binomials the same? No. Can I switch the order of the second binomial to match the first one? Is there a commutative property of subtraction? And the answer is no, because 3 take away 2 gives me 1, but 2 take away 3 gives me negative 1. So there comes a point where you're saying, well, I'm kind of stymied here. But we actually can do something to get those two binomials to match. What can we do, Lucas?
Multiply one side by negative 1.
Okay. So if I took this guy and I factored out a GCMF of negative 1, it makes the x positive and the y negative, which now matches the other term. The question is, what do I do with that negative 1? Okay, what do I do with that, Amanda?
Times it by 3.
Say again?
Times it by the positive 3.
Yeah, he is now, really what this problem says is 3 times negative 1 times x minus 1. So now my problem is written this way. I haven't touched the first guy at all. 4x times the quantity x minus y. But for the last guy, I've got a lot of changes. I have 3 times negative 1 is negative 3. And then I have the x minus y. Okay? So that's what we have to do, is we have to make sure that we take that negative and that we attach it by multiplication with whatever's in front of the binomial. All right. Now, do we have a match of the two binomials? Do we have x minus y and x minus y? Yeah. So what we're going to do is factor out the x minus y. So that gives me an answer with x minus y out in front. And what would the binomial be that incorporates the leftovers? Jason?
4x minus 3.
And 4x minus 3 is right. That's it. Notice I don't have any difference of squares because x isn't a perfect square, 4x isn't a perfect square, so that's as far as I need to go. Okay? But that would be nice if they already did half the work for you. So you do have to watch out for this sign. That made it a little bit trickier. What if they just give you a string of 4 numbers? So like the example we started with as a warm-up. So let's do it. Everybody ready? I'll pause. Okay, let's try. What if they don't give us anything? What if we just have a big, huge string of problems? So we have 5a minus 5an minus nx plus x. And we had talked about, well, if there isn't a GCMF for all of them, which, by the way, is step number 1, is there GCMF that all 4 have in common? Because it will happen. Just forewarn you. And if the answer is no, is can you put them in groups of 2 and look for a GCMF? So we tend to just group them, the first 2 and the second 2. Okay, so look at the first 2. What do they have in common that I can pull out? Allison? A 5 and an A. Now, here comes a problem with the second grouping. Notice, if you did 5a divided by 5a, you would get what? 1. So your hope is that your second binomial is going to have 1 in the front when you pull out its GCMF. What's the GCMF in the second group? X. If you divide minus nx by x, you get negative n. So that poses a problem. So here's what you have to watch out for. Anytime you have a negative in the middle, in addition to pulling out a monomial that they have in common, you also have to pull out the negative. Now, in addition, what else do they have that's the same? They have an x. So I'm going to go step by step through this one, since it is a little weird. So the first grouping, we have 5a. Left behind is 1 minus n. Now I'm going to pull out a negative x. So that's going to end up changing all my signs because of the negative. So a negative nx divided by a negative x will give me a positive n, right? 2 negatives make a positive. And then x divided by a negative x is going to give me a negative 1. Okay? Totally strange what just happened. Here I thought, man, we're going to get a match. Guess what? We don't. How can I get n minus 1 to look like 1 minus n? What am I going to do there? Patrick?
You factor out negative 1 from the negative x times 1 and minus 1.
Oops. When I factor out a negative 1, the n becomes negative, the 1 becomes positive. Okay? And then remember what we said we do? We take that negative 1 and we multiply it up to the top. So here's what your problem looks like right now. 5a times the quantity 1 minus n, and then it's going to be plus x times the quantity 1 minus n. Now they both have, oops, 1 minus n in common, so we're going to factor that out. So we get the quantity 1 minus n And then all we do for the second bit is we take all what remains. So that's the 5a and the x. And there's that answer. Okay. I think we have time for one more. So let's do this one. 10a squared plus 20ac minus 6a minus 12c. All right. Looking at that, do we have a GCMF? Oh, we do. They're all even, so I can pull out a 2. So this is what I'm talking about. You always have to be looking for everything. That's the deal with fluency, is they expect you to be able to look for everything. So we pull out a 2, and we get 5a squared plus 10ac minus 3a minus 6c. Okay. Now we attack grouping. What do 5a squared and 10ac have in common? 5a. And then what do negative 3c and negative 6, there's negative 3a and negative 6c, excuse me, have in common? Ooh, remember him. He says you've got to pull out a negative, and they have a 3 in common. So here's where we're at. Now I got to employ some brackets, because I'm going to pull out the GCMFs for each of those pairings. So let's see, 5a squared divided by 5a is a, plus 10ac divided by 5a, well, 10 divided by 5 is 2, ac divided by a is c. Now I'm pulling out a negative 3. Negative 3a divided by negative 3 is a, and negative 6c divided by negative 3 is positive 2c. You should be able to see inside the brackets. They have an a plus 2c in common. So notice this time when I pulled out that sign, that negative, what I ended up with in my binomial was exactly what I needed. So you just have to stay flexible in what you see and do what you need to do to get to your answer. So here's what we got left. We still have the 2 out in front. We now have the a plus 2c. And now we just grab the last remaining pieces. Let's make it this color. We've got this coefficient, and they form their own binomial. Very colorful. Looks like Mardi Gras colors. Okay. Yes, Ethan. No, we don't distribute the 2. We leave it as a GCMF out in front. Okay. Hold on, guys. There's questions being asked. Amanda. I'm going to make you do all of them. Okay? All right. Good luck with your homework.